Hello physicists and welcome. In this session we'll be looking at moment of inertia, also known as our rotational inertia or rotational mass. Let's get started. Newton gives us a relationship between force, mass, and acceleration in the linear world, given by the most famous equation, F equals ma, but we could use that to isolate or figure out any of the variables. We could look at mass being our measure of inertia as being our force divided by our acceleration. Just a couple of reminders of things that link our linear and rotational world. First is that if we have a force at some distance from an axis of rotation, it produces a torque or a twisting force, and a relationship between acceleration and angular acceleration is related by the radius of our angular acceleration. All right. So I'm going to take that our equation of F equals ma. I'll multiply each side by r, okay, and then I'll substitute my radius times force with torque, and then substitute the value for acceleration with our angular acceleration, RA. Now I'll go and combine terms. So I find out that torque is equal to mass times the radius squared times my angular acceleration. Let's go ahead and divide each side by that angular acceleration. And I have this value where I have the twisting force divided by angular acceleration is equal to mr squared. And so really then mr squared is our rotational inertia. And thinking about how difficult something is to rotate, not only is it a matter of the mass, but it's how the mass is distributed. The further the mass is from our center of rotation, the more difficult it is to change its rotational rate. Okay. And this is known as the moment of inertia. So a handy equation for that is I, our symbol for moment of inertia, we can call it rotational mass or rotational inertia, is equal to mass times radius squared for a discrete point. Okay. So let's take a look at that. So I do have my equation I equals mr squared, and if I do have an object out over here at some distance r, I can figure out its moment of inertia by using this equation, mass times radius squared. But what happens if I have multiple blocks? I've got various blocks. I need to take, let's say I've got M1, M2, M3, M4 at various radii, at R1, at R2, at R3, and at R4. How can I figure out the moment of inertia for that? I just add up all of the discrete elements to figure out what the total moment of inertia is for our masses at discrete points. But now, what if I end up having a distributed mass? I'm looking at rotating about this point, and I have a uniform rod. Let's say it has a mass m, and it has some length L. How do I end up figuring that part out? So for every little chunk here, I've got some amount of mass. That mass over the length will give our mass per unit length times that little bit of area there will be equal to our little bit of mass. So we could look at that equation for summing up our mass over a distance and come up with this integral. We covered that earlier before in class as well, that our moment of inertia is the integral of r squared dm. So now we have to take a look at how do we figure out dm, and we've done some work here. I keep making my intervals smaller and smaller, and eventually my change of mass, or that little bit of mass in this area here, dm is equal to the mass per unit length times that little bit of mass I have there. So let's go ahead and we'll change this around. So I'll say, that's r squared m over L dr, and now I can integrate that. I'll bring the ml out in front. Those are constants. Take the integral of r squared dr is equal to m over L r cubed over 3, and we'll evaluate that from 0 all the way out to L. So from 0 to L, let's go ahead and put those numbers in there. So I have m L cubed over 3L. That'll cancel. Hey, so for a distributed mass, a long slender rod like this, my value becomes ml squared over 3. Hey, let's change this up a little bit. We're going to, instead of rotating about one end, we're going to rotate about the middle. It means that much of our mass is closer to that center of rotation. So let's take a look at that. Hey, but just to cut things down, hey, remember this, all right? That integral. Hey, so we remember for rod, this is going to become r squared m over L dr. When you take the integral now, we're going to look at m over L integral r squared dr. And instead, we're going to call this the 0 point. So if we're going from negative L over 2 to L over 2. So our integral, our limit of integration, L over 2, or minus L over 2 to L over 2. Let's go ahead and I have m over L r cubed over 3. And I'm going to go from negative L over 2 to L over 2. You can probably do that as well, but we'll find out this comes out to m L over 2 cubed over L times 3 minus m negative L over 2 cubed over L times 3 works out to what? We have ml squared over 24 minus a negative, so I get plus ml squared over 24. So for the moment of inertia, or the difficulty in trying to rotate this, I come up with a numeric value of ml squared over 12. Hey, let's take a look at another distributed mass, and that would be for a disk. So let's say we have a disk of radius r, and what else is special about this? Okay, we're going to say that the mass is uniformly distributed over this. And we're going to try rotating it about the center. Okay. Hey, so now we have that same relationship, that the moment of inertia is equal to the integral of r dm. But now we have to figure out what dm is for a disk. Okay. Hey, so let's take a look at this. Why don't we take a look at, hey, a thin annular region like this. And we're going to say that we go from a radius of r out to r plus delta r. Okay. Hey, so let's see. So my little bit of mass here. Okay. If I have uniform mass, let's see. Uniform mass will be. So our little bit of mass is going to be equal to the mass of the whole disk over the area of the whole disk times our little bit of area. Okay. Hey, so our area for a disk is pi r squared, and for our little bit of area, we're going to have pi r. Whoops, sorry. Oh, hold on this. Okay. Sorry about that. Let me erase this for a moment. There we go. All right, a little bit cleaner. Okay. Pi. Now our r is little r plus delta r squared. That would be the area inside our larger portion of the ring minus pi r squared. Let's go ahead and simplify that. All right, so I get what? Pi times r squared plus 2r delta r plus delta r squared minus pi r squared. Let's go ahead and simplify that. You can see that, hey, this portion and that'll cancel. So what do we get? Okay, this delta r, remember r gets smaller and smaller, and by squaring it we get something that's really, really small, so we'll just ignore that. We're going to say that goes something like 0. So our little area is going to be 2 pi r delta r. And that's equal to r delta a. So let's take our integral. Our integral is now going to be r squared, and then let's see over here, our delta a is now we're going to have m over a 2 pi r delta r. Okay, so we can, now our a is actually pi big R squared, right? And our delta r, we're going to make it really small, so I'll just make it dr. So we'll take the integral of, I got an r and an r. It looks like we're going to have m over, how come this isn't writing? Over, I'm right at the edge, that's what it is. Hold on a moment, let me adjust this. All right, let's move all those constants out in front. So we're going to get 2 pi m over pi r squared. We're going to take the integral of r cubed dr evaluated from 0 to r. One of those things, I'll leave this to a student to evaluate, but we can take a look at what does this end up being. 2 pi m over pi r squared. We'll see the pi's and pi's cancel, for r to the 4th over 4 evaluated from 0 to r. What do we get? 2 m r to the 4th over 4r squared gives us, that'll become squared, that'll disappear. I get mr squared over 2. Hey, so our moment of inertia for a disk. Hey, we have one more challenge here I want to take a quick look at, and that's the idea about if we have the moment of inertia about any axis. It isn't necessarily on the part or in the center. So let's say we have that same disk we were just working with. It has a radius r, but instead of having our rotation at the center, we want to have the rotation out off the disk someplace. And it's some distance d from the center of that. Hey, we could look at our integral here, the integral of r dm for this distribution, which would be a real mess. All right. Hey, but we find that we can end up making this a little bit cleaner if we end up using something referred to as the Parallel Axis Theorem, where I look at the moment of inertia about some position is the moment of inertia of the object around its center of mass plus mass times distance squared, as if all of the mass was centered at the center of mass of our part. This is known as the Parallel Axis Theorem. Let's go through maybe a quick calculation of this, all right? So I'll say my disk has a mass of 2 kilograms, has a radius of 4 meters, and the distance from this point we want to check the rotation to the center of our disk is 6 meters. So my I for the center of mass for a solid disk is mr squared over 2, in this case, mass 2 kilograms, my radius 4 meters squared, divided by 2, let's see, 16, oh, this should be pretty easy, I'll cancel that. It's going to be, so this part's going to be 16, notice the units, kilogram meters squared. Hey, now because we're off the axis or the parallel axis, our moment of inertia will be md squared, so our mass 2 kilograms, our distance 6 meters squared. What do I get there? 3672 kilogram meters squared. Let's go and add those up. So our total inertia about x is 72 plus 16. What's that? 88 kilogram meters squared. Hey, so the parallel axis theorem makes it a whole lot easier when we have our center of rotation at some place where it's difficult to figure out what that moment of inertia is. So for now, that's physics.